Okay, so this is to help you with question 1 of the Geometry Unit 3 test. Um, Here's the information that you have. You know, ABCD is a parallelogram. AE is 6 centimeters, AD is 14 centimeters, AF is 5 centimeters, and EF is 3 centimeters. For part A, it says in two-column format, prove that triangle AEF is congruent, or I mean, excuse me, similar to triangle BFC. So one of the ways that you can show that two triangles are congruent is by showing that at least two of the angles are the same in each triangle. And that's called the angle-angle postulate. Angle-angle similarity postulate. And so that's what we can use here. And I'll show you how. I'm not going to write the proof for you, but I will show you how those two triangles are congruent and have two angles congruent. So the hardest thing I think to see, let me change colors, is where the parallelogram part comes in. So first let's make sure we know which triangles we're looking at. We're looking at triangle AEF up here. And we're trying to show that this triangle is similar to this one over here, BFC. So we're trying to show that those two triangles have at least two angles that are the same. So right away, hopefully, you remember the vertical angles. Okay, anytime you have two lines that intersect, like we have here, and the angles are across from each other, those are vertical angles and they will always be equal. Where the parallelogram part comes in is in a parallelogram, which this right here, ADCB, is a parallelogram. If you remember, one of the properties was that the opposite sides are parallel. And so if I highlight this line and this line, those lines are parallel to each other. If you look at this line, it crosses those two parallel lines. And hopefully you remember that that's called a transversal. And anytime you have a transversal crossing two parallel lines, you know a bunch of angles are the same. Alternate interior, corresponding, all those names hopefully will come back to you. But if you look at angle AEF right there and angle DCF right here, or excuse me, not DCF, let me well, if I can get that, there we go. Angle FCB, those are alternate interior. You kind of have to tilt your head to the left a little bit to see that, but they're both in between the parallel lines and they're on opposite sides of this transversal, and that's called alternate interior. And so as you can see, what we've shown now is that two angles in triangle BFC are the same as two angles in triangle AEF. For part B, it says assume triangle EDC, which is right here, is the image of triangle EAF under a dilation. So here's triangle EAF. And I drew them out down here. So in other words, the way that that's worded, when you hear that one triangle is the image, that means that's your final product. So this is the image. This is where you're going to end, and this is where you started. Okay, this is the pre-image, and this is the image. So this is where you started, and this is where you ended. It says, is the dilation an expansion or a contraction? Well, if you look at the pictures, if you figure out which one's the pre-image and which one's the image, you're going from a smaller triangle to a bigger triangle, and that's going to be an expansion. And then to figure out the scale factor, you're going to just want to make the ratio of two sides. So if we look back at this picture, we could figure out what side ED is of the larger triangle by adding 14 and 6 together. And then we can figure out that same side for angle EA, because if you're under dilation, these two triangles are automatically going to be similar, and so you want to make sure that you have two sides that are the same so that you can make a proportion to find your scale factor. Now you can either do 6 over 20 as your scale factor, or you can do 20 over 6 as your scale factor. And I'm going to let you think about that and figure out which one of those is correct. Just remember, we are under an expansion, so think about how that would give you a hint there. For part C, it says calculate DC and show your work. Well, what you're wanting to do here, because you know that these two triangles are similar, you know that the sides are proportional. So if you look at DC, over here in this triangle, that is corresponds to side AF, and you do know AF. And so you know three sides, you're missing this side, you should be able to set up a proportion and find that. For part D, if you're not familiar with the side-splitting theorem, you should get familiar with the side-splitting theorem. But it says, let's say if I have a triangle here and another triangle, or a line splits that triangle in half. And let me just make up some letters here. It says you could do x over y, and that's equal to z over a. Okay, so that's the side-splitting theorem. And so you can see that similar picture showing up right here. And so you want to use that idea of the side-splitting theorem and this formula here to help you with part D. And then for part E, the ratio of the areas of triangle EDC to triangle EAF. Well, the ratio of the areas is always, so we'll call this area, we'll just say area 1 over area 2, whatever your areas are. The ratio of those is just this fraction. So this is the ratio of areas. You just put one area over the other, is equal to your scale factor, which we call T, squared. Just like to help you remember this, we're dealing with areas. The units on area are squared, and so you want T squared over here. So remember, T is your scale factor. We already found that scale factor in part B. And so if you use that scale factor here, you're going to be able to find the ratio of these areas. And remember, this is the ratio of the areas. So once you do T squared, that is this answer. The ratio here is equal to this. So once you calculate T squared, that's what part E is getting at. So I hope that helps with question 1. A lot of these ideas, especially up here, this formula right here, will definitely carry over to question 2. So question 2 talks about the scale factor, which is the same concept as what we did down here. And then you want to, part B is the area of the bases, the ratio of the area of the bases. So again, you're going to use this formula in question 2, and then part C of that question 2 is talking about the volumes. So remember the idea I said, if area, the units are squared, well, think about if you switch the ratio of the volumes, volume 1 over volume 2 would be equal to T cubed, because the units on volume are always cubed. And then that should help you quite a bit with part 2. So part 2 is similar. It's just really using these scale factor, area, volume ideas. So good luck, and let me know if you have any more questions.